Okay, let's now look at the definitions of apparent power and power factor. And as we're going to see, they fall right out of the complex power equation. So let's consider that equation. If we work in RMS phasors, the complex power is VRMS times IRMS complex conjugate. Let's do some decomposition of this. We know that VRMS, I'll just write that in polar form as VRMS theta sub V. IRMS is the magnitude times theta sub I, and IRMS complex conjugate is equal to the magnitude at a phase angle of minus theta sub I. So these are just the RMS phasors and the complex conjugate of the current phasor, all written in polar form. So given this, I can rewrite this. This is equal to VRMS IRMS times theta sub V minus theta sub I if we combine the magnitudes and the phase angles in the polar form. We've already seen a development this just very much like this in our previous module. But what is this, VRMS IRMS? Clearly, this is the magnitude of the complex power. And I can just write it that way. That's magnitude of complex power at a phase angle of theta sub V minus theta sub I. We give a name to that magnitude. The magnitude of complex power, which is just equal to the product of the magnitudes of the RMS current and voltage across any element, will be equal to the apparent power. And apparent power, just like complex power, has units of volt amperes. Which means that I can now rewrite this. I can decompose this and turn it into a rectangular form. And in this case, what I get is that S is equal to the magnitude of S times cosine theta sub V minus theta sub I plus J times the magnitude of S times sine of theta sub V minus theta sub I. All right? And so from this, I got a couple more definitions I can pull out of this. Let's look at this equation here just for a moment. The way I've written this. Let's define the following. All right. I'm going to define theta sub V minus theta sub I. That is called the power factor angle. The cosine of theta sub V minus theta sub I is the power factor. And we typically abbreviate that as PF. Sine of theta sub V minus theta sub I is the reactive factor. So I can substitute and I can rewrite this, where S is equal to the magnitude of S times the power factor plus J times the magnitude of S times the reactive factor. But we know that's equal to P plus J times Q by definition. And so from here, I can write two simple equations. P is equal to the real part Q is equal to the magnitude of S times the reactive factor. And therefore, apparent power is either equal to P divided by power factor. It's also equal to Q divided by reactive factor. So all of these identities come right out of this equation, right out of this definition. All right? Power factor. Why do we care about power factor? Let's consider that. What does power factor tell us? Well, it turns out that the power company cares very much about power factor. Power factor tells you if a load is purely resistive, purely reactive, or some combination in between, some mixture of resistance and reactance. So in other words, if we think about this, power factor, which is just cosine theta sub v minus theta sub I, power factor will be equal to unity. In a resistor, theta sub v is equal to theta sub I. Cosine of 0 is 1. So power factor is equal to 1 for a purely resistive load. So if your load is nothing but a resistor, then the power factor will be equal to unity. If you have an inductor or a capacitor where theta sub v minus theta sub I is either plus or minus 90 degrees, then cosine of plus or minus 90 degrees is equal to 0. And therefore, power factor is equal to 0 for a purely reactive load. So if I've got either L or C, my power factor is going to be equal to 0. If I've got a mix of both resistance and reactance, a resistor plus an inductor or a resistor plus a capacitor, then I'll have a power factor somewhere between 0 and 1 for a resistive plus a reactive load. We also note that the average power is equal to the apparent power for a resistive load. Because keep in mind, P is equal to VRMS times IRMS times theta sub V, times cosine theta sub V minus theta sub I, which is, for a resistor, this is equal to unity, and so this is just equal to the magnitude of the complex power. And so the average power and the apparent power are the same for a resistor. For all other loads, for anything that contains a reactance, then the average power is less than the apparent power. Now, if we're going to describe power factor, we need something else, because there's an issue we have to deal with. We note that cosine of x is equal to cosine of minus x. A cosine of plus 45 degrees is the same as a cosine of minus 45 degrees. You get the same cosine. So if you're describing a power factor, you can't tell the difference between a power factor with a positive power factor angle or a negative power factor angle. You need something else to fully describe a power factor. We must define what's called lagging versus leading power factor. And we do this to distinguish between inductive versus capacitive loads. So here's how we apply the definition. A lagging power factor occurs when theta sub v minus theta sub I is positive. In other words, the current lags the voltage. And this happens in an inductive load. A leading power factor occurs when theta sub v minus theta sub I is less than 0, when it's negative. In other words, I leads V. Current leads voltage. And in this case, that indicates a capacitive load. So let's do a couple of examples. Let's do an example to illustrate this. Let's assume we've got the following circuit. So I've got a load. And for this load, there's a current and a voltage associated with that load according to the passive sign convention. All right? And I've got the following values for V and I. For this example, let's let V equal to 100 cosine omega t plus 15 degrees volts. Let's let I be equal to 4 times cosine omega t minus 45 degrees amps. And let's calculate all of the values we've been looking at so far. Let's find P, let's find Q, let's find the power factor, and let's find the apparent power. And in this case, to do this, we're simply going to convert V and I to phasors and then use the complex power formula. So therefore, V, going to phasor format, is just equal to 100 at a phase angle of 15 degrees volts. I is equal to 4 at a phase angle of minus 45 degrees amps, and therefore I complex conjugate is equal to 4 at a phase angle of plus 45 degrees amps. And in this case, since these are not RMS values, I would call them VRMS and ARMS, voltage and current RMS. Since these are non-RMS values, then S will be equal to V times I complex conjugate divided by 2. Obviously, if these were RMS values, I wouldn't need that divided by 2. And in this case, this is equal to 400 at a phase angle of 60 degrees divided by 2 is equal to 200 at a phase angle of 60 degrees volt amperes. So now everything kind of falls out. The apparent power is just the magnitude of the phasor. 200 volt amperes. That's my apparent power. In addition, S is now equal to 200. I've got a 60-degree phase angle, so cosine 60 degrees plus J times 200 times sine 60 degrees. So I'm just converting this to rectangular form. This is my power factor. This is my reactive factor. And this is equal to 200 times 0.5 plus 200 times 0.866, which is equal to 100 plus J, 173.2 volt amperes. So I did nothing but just take this and convert it directly into rectangular form. And this is equal to P plus JQ. And therefore, P is equal to 100 watts. Q is equal to 173.2 VARs. We note theta sub V minus theta sub I is positive. It's equal to 60 degrees. All right? Which means that my power factor is equal to 0.5, this numerical quantity, lagging. In other words, this is an inductive load. Now, this shouldn't be any surprise. Look at Q. Q is J 173.2. So Q is a positive value. Positive VARs are generated or basically associated with an inductor. Negative VARs with a capacitor. We said that before. So you would think this is lagging, right? It is a lagging, it's an inductive value. So this agrees. Okay? Now, once again, I want to emphasize this. If Q is greater than 0, if we have a positive value of Q, you're going to have an inductive load and you're going to have a lagging power factor. If Q is less than 0, you're going to have a capacitive load, which will be a leading power factor. In fact, let's do an example with a leading power factor. Let's do another circuit. Let's see if these equations make sense the way we've defined them so far. So I've got a source connected across the following load. And in this case, this source is 120 at a phase angle of 0 degrees, volts RMS. Notice in this case, the source is RMS. So all the currents and everything else in the circuit will be RMS as well. This is 50 ohms. This is minus J 10 ohms. Let's calculate all of our quantities for this, all of our complex power quantities. So in this case, I'm going to have a phasor current I. And I is going to be equal to, well, in this case, this is just 120 volts in rectangular form, or 120 volts RMS. So this will be, I is going to be equal to 120 divided by, these two are in series, 50 minus J10, which will be equal to 2.308 plus J 0.462 amps RMS. The current's got to be in RMS. The voltage for the source is in RMS. And therefore, this will be equal to 2.353 at a phase angle of 11.31 degrees amps RMS in polar form. And so now the power, the complex power of the load is just going to be equal to the voltage of the source, because the source voltage is across this load, times I complex conjugate, the complex conjugate of this current. And this will be equal to 120 at a phase angle of 0 degrees times 2.353 at a phase angle of minus 11.31 degrees. There's no factor of divide by 2 in this because I'm operating with RMS phasors. And this will just be equal to 282.4 at a phase angle of minus 11.31 degrees volt ampere. Now, if I convert this to rectangular form, I'll get the following. In rectangular form, this becomes 276.9 minus J 55.4 volt amperes. Okay? This makes sense. There is my real power. Here is my reactive power. So in this case, P is equal to 276.9 watts. Q is equal to minus 55.4 vars. Makes perfect sense. That is a capacitor. It's going to have negative vars, not positive vars. And in this case, we also note that the power factor angle, minus 11.31, is negative. So negative power factor angle, negative impedance, negative vars. The signs always carry through. And so in this case, what I will get is the power factor is equal to cosine minus 11.31 degrees, which is equal to 0.981, and in this case is leading. Now, a couple of things to point out. Typically in industry, you will see lagging rather than leading power factors. And the reason why is most big industrial loads, for example, motors and the like, are typically going to be big inductive loads. They have windings in them to generate magnetic fields. So when you look at like electric motors, you expect those to be inductive. You think about it, you're running your vacuum cleaner. There's an electric motor in there. Your home air conditioning system. There are fans running. There's a compressor running. Your refrigerator, another compressor. These are all mechanical devices that use motors. And so most big loads are going to be inductive with lagging power factor. Leading power factors are relatively rare. All right? One other thing to consider is this: power conservation. For a DC circuit, at the beginning of the semester we said the sum of all powers must be equal to 0 in any circuit. The same is true now. For an AC circuit, the sum of all the complex powers in a circuit must be equal to 0 as well. And what this means is the sum of the real powers must be equal to 0, and the sum of the reactive powers must be equal to 0 as well. So, as you might guess, power conservation still holds. All the real parts will cancel, all the imaginary parts will cancel out, and they'll basically all sum to 0 if you've solved the circuit correctly. So just worth mentioning. Hopefully this was kind of obvious to everybody, but conservation still works. Okay. Well, we defined all these interesting terms: apparent power, power factor. Well, why does the power company care about these? I mean, power factor means a lot to the power company. Why? Well, there's a reason for that, and we'll get to that next time. Turns out that we need to consider a technique called power factor correction to keep from getting surcharged by the electric company. We'll talk about that next time.